Good afternoon, everyone. So today I want to feature a music that is "Here You Come Again." Right, here is the YouTube link, so you can listen to this music if you like. So I selected this song because today we will just still keep talking about the superposition method. Since we introduced the superposition method last time, we used it to calculate as an alternative method, right, to calculate the deflection in simple beams. So today we'll extend this method and use the superposition method to calculate the deflection in combined beams, just more complicated beams as compared to cantilever and simply supported beam. That is our objective today, calculate deflection in combined beams using superposition methods. So 2 days ago, we talked about the superposition method and use it to calculate the deflection in simple beams. But before that, we introduced the deflection, the calculation method for deflection using integration method. So if you're given a beam, a random beam as shown below, any one of them, if you want to use the integration method, you need to follow several steps. Right, first of all, you start from the loading distribution, and you do one integration to get the shear forces, and do another second integration, you get the bending moment. From the bending moment, you do further integration, then you get the slope, and you do the fourth integration, you can get the deflection distribution function. Right, so in each of the steps, you have some assumed constant, and you need to use the boundary conditions to determine those constant values. This is very complicated methods. Right? So I said this is perhaps the most difficult part in mechanics and materials. The good news is that these methods, integration methods, will not be tested. So I may give you a couple of homework or exercises so you can know how to use this method to calculate deflection. But this will help you understand the mechanisms of these equations, how they were derived. Right? But simpler, you can use the superposition method to solve the deflection problems. Since we have used the integration method to determine the deflection functions for a lot of cases, and we summarized them into two big tables. You can find the relevant situation, select the correct equation, and use them. Superposition, you can add them together or subtract one from the other one, and those are called superposition. So let's look at these four examples listed below here. And in the first one, it's a simply supported beam subjected to the combined loading. Of course, if you want to solve this problem, you just need to split it into two parts. Well, obviously, the first part will be uniformly distributed load. Let's see, it's W. And the second part will be concentrated load P. Right, so you can use beam 1 and beam 2, right, plus them, add them together. You get the overall effect. Right, you can calculate the overall deflection at a random point. So from these two tables, of course, for beam 1, you get equation 12. For beam 2, you get concentrated load, you get equation 3. Well, you can use these two equations to calculate the deflection of at any random point. If you only care about the maximum deflection, that is at the middle span, if you only care about this point, you can directly use equation 11 and equation 2. Right? So add them together, you will get the overall deflection. Well, for the second beam, obviously it's a cantilever beam, so you can just split it into two parts. The first part subjected to distributed load W, and the second part subjected to concentrated bending moment at the free end M. Right, here you have beam 1 and beam 2. Right, so for this case, so you can find in this cantilever beam table, this is our beam 1 and this is our beam 2. Right, they can use equation 30 and equation 27 or equation 29 plus 26 to determine the deflection at a random point or the maximum deflection at the free end. Well, the third beam is very similar to the second one. So you can split it into two cases. The case 1 will be a uniformly distributed load, and the beam 2 will be a concentrated load P at the free end. Right? Just add them together. Right, so the only change will be the beam 2 need to be here. Right, so this is the beam 1 and that is beam 2. We can use 30 plus 21 or 29 plus 20. And the fourth example, that is our last example 2 days ago. Right? So this one, you cannot simply split it into two cases, since it's just a distributed load. So here you just need to use your imagination. So imagine that at the beginning, you have a fully distributed load. W. And the second case, you have a distributed load covering the first half of the beam. So here you just need to do a subtraction rather than plus. Right? So in the first case, of course, you still use your equation 30 or equation 29, depending on where you are determining. Let's see, so we're determining the maximum bending, the maximum deflection at point C. Okay, so you just use equation 30 here, equation 30 to determine the maximum deflection at point C. Then in the second, in beam 2. In beam 2, of course, we still use equation 30. Right? We still use equation 30. But after bending, this first half will be bended to here. But at the point B, you can determine the slope. You can determine a slope, right? You can also determine the deflection here. This is our first component. Let's see here, you determine a delta 1. And here, this is the first component, delta 2, 1. And it will be transferred to here. Right? And you can also use the equation 28. Right? Use the equation 28 to determine the slope at point B. Here at point B. Here you can get a slope theta at point B. This is also the value of this angle here. Okay, so based on this triangle, now we can build a triangle. Okay, in this green triangle, you know this angle. And you can suppose that this angle is very small, and you know the section BC will not be bended, right? In beam 2, section BC will not be bended. It will keep straight. So it will only be rotated by an angle theta B. It will not be bended. So just in this triangle, suppose this theta B is small enough. So the second component of deflection here, delta 2, 2, delta 2, 2 will be calculated by theta B by BC. Okay. So now you can just determine the overall deflection at the point C by adding these three things, right? It's delta 1 plus delta 2, 1 plus delta 2, 2. This is how you determine the deflection, the maximum deflection in the fourth case. And here are these two big tables that we'll use to determine the deflection in loaded beams based on superposition method. So today we will we'll extend this method, extend the superposition method to solve the deflection problems in combined beams. Now here's one example of the combined beam. It's overhanging beam, right? So in this case, when we talk about the combined beam, we will discuss determining the deflection in beams that require splitting. Well, you need to splitting the overhanging beams into cantilever beams and simply supported beam. So the two situations will be discussed separately. You need to split them and then calculate the deflections based on our method in the last section. To calculate their deflections, then consider how to combine them together. And you can calculate the deflection in the cantilever parts and deflection in the simply supported parts. Let's see this example here. It's an overhanging beam. So obviously, if you want to split it, you can split it from here, from the connection point C. Then now you will get a CD. The CD, you can consider that CD is a cantilever. CD is loaded by a load PD. Right, then this section AC will be the simply supported part, and it's loaded by a loading PB. Right. So here, if this cantilever part is loaded only by a PD, so you can simply calculate the deflection at point D by using our equation. You can find the correct equation from the big table. It's likely to be example equation 21. Right here, it is 21. But is that all? We will see later how can we calculate the deflection of this part. Okay, but let's look at the simply supported part. AC is subjected to a PB, but is that all? Is that all of the external loading that the section AC is subjected to? Actually, a part of this PB. Thinking about that, if we split it from here, so apart from this PB, when you separate this part CD, when you load it by PD, actually to balance the PD reaction force here, MC, will be generated. Right, to balance this MC, the MC will also be applied to this simply supported part AC. So you have MC here and MC here. So this simply supported part AC will also be subjected to a bending moment at the point C. This is MC. Okay, so if you are calculating the deflection at a random point in AC, you just need to consider these two external loading. This will be simplified into a case in our previous section. One simply supported beam subjected to two loading. You split it into two parts, then add them together. So you get the deflection, the overall effect in the simply supported part AC. But how about the cantilever part? The cantilever part had only one loading PD, but as we said, these two parts, the simply supported part and the cantilever part, will be connected at point C, right? So the PB and MC will not be able to bend section CD because section CD, the point D is not restrained. So it will not be bended. But as the CD is connected to AC at point C, so it will be rotated. Right? This section CD will be rotated in some way. And just look at this AC. So when this AC is bended by PB, it will be bended in this way. Then at this point C, you have a theta C1, right? You get a slope. So use this slope, since we said this CD will only be bended or will only be rotated. So based on here, you can build a triangle, so you can calculate the deflection at point D due to this rotation, right? And this AC will also be bended due to this moment MC, right? So it will be bended in this way. So after this bending, of course, you will get another triangle, right? So this is the downward deflection. The first component here is the upward deflection. Right here you will get a downward deflection, and you can calculate the theta C2, the second components of the slope. Then from the second triangle you can get another component of the deflection. Then for this cantilever part, you have three components to consider. Right? The component 1, component 2, and component 3. So here's the summarize. Right? This the same thing. Then you can split it, then get a cantilever part. So you can calculate the first component delta 1 based on simple equation in the table. Then the second component is just consider the simply supported part and the concentrated load PB. So you get a theta 2 here, and this angle will be the same with equal to theta 2. So in this triangle, since your CD, this is CD, will keep straight, but it will be rotated, right? So this triangle, so you can calculate the second component. This is the first component, second component, delta 2 prime. Right. Then the third case, it's just a simply supported part subjected to a concentrated bending moment at point C. It will be rotated. You can calculate the theta 3. Again, here this angle equals theta 3. So here this will be the CD, and here the second triangle. So here you can calculate the delta 3 prime. Right, so here this is overall deflection will be equal to delta 1 plus delta 2 prime plus delta 3 prime. Okay, this is several steps. Right, so step 3 split it, and then step 2 determine the direct deflection, the first component, and step 3 determine two theta values. Right, this consider all effect. It may be more than two if you have two loadings. Right, consider effect of all external loadings separately. Then don't forget the effect of the internal moment that comes from the cantilever beam. Then in step 4, you just use two triangles. You have theta 2, theta 3, and you have LCD. So you can calculate the second and the third component of deflection. Then the last step, you add all of the three components, get the overall deflection. So that is the steps to determine the deflection in the cantilever part. So here, this slide, we're showing how to determine the deflection in the simply supported part. Okay, the same deflection, the same splitting, right? It's into one cantilever beam, two simply supported beam. As we analyzed before, well, this beam 1 will not affect the simply supported beam. All of its effect has been reflected by this concentrated bending moment MC. Okay, apart from this, this beam 1 will not make any change to this deflections in the section AC. So we can ignore it. Only consider beam 2 and beam 3. Right, this beam 2 is easy. There's one simply supported part subjected to a concentrated PB. And the beam 3 will be one simply supported beam subjected to a concentrated load MC. You can directly find equations for them from the simply supported beam table. Right, let's get delta 2 and delta 3 at a random point, then add them together. Okay, so you will get the overall deflection at a random point, or at the mid span, or at the point the PB is loaded, depending on your purpose. Okay, these are the two tables, the same as the previous section. So we will solve several examples together to illustrate how to use these two tables and the algorithms we just talked about to solve the deflection in combined beams.